Ito ang beat, sabay-sabay. Ito ang beat, bawat sablay. Pabilis ng pabilis, pag-remix, pag-remix. Yes mo na, yes mo na. Nalilito, nalilito, nahihilo, nahihilo. Kokoto, 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 kokoto. Oh, koko yan. Ulitin natin, please.
But our story begins with heat as energy. One day, about 200 years ago in Munich, Germany, a large crowd gathered round a man called Count Rumford, who was busily boring out the barrel of a cannon. Now, this was a pretty common sight in those days, so why the crowd? Because Rumford had fitted a box round the tip of the drill, and the box was filled with water. And after the barrel had been turning on the drill for some time, the water became so hot that it began to boil. The crowd was astonished to see all this heat apparently coming from nowhere. And Rumford was pretty excited too, because he saw that the only thing that was producing the heat was the movement and the friction between the barrel and the drill. Whenever there is movement and friction between two objects, you get heat, whether you're boring the barrel of a cannon, rubbing two pieces of wood together to make a fire, or simply rubbing your hands together to keep warm. This is because when two objects move against one another, the molecules in these objects go faster. And we know that it's the speed and the mass of molecules that determines quantity of hotness or heat. Fast molecules are hotter than slow molecules. And they can use their rapid movement to make things hot for any other molecules they come in contact with. In other words, fast molecules have the ability to do work on other molecules. Now we know that ability to do work is the definition of energy itself. So when molecules move fast, not only is there a lot of heat, but there is also a lot of energy being transferred from molecule to molecule. But since movement is a form of energy, and the movement of molecules and heat are really one and the same, it follows that heat itself is also a form of energy. Now, when we looked at temperature, we saw that its unit of measurement is the degree Celsius. What is the unit of measurement of heat? Well, what is the unit of measurement of energy? The joule, of course. So logically enough, since heat is energy, the unit of measurement of heat is also the joule. We know that 1 joule is the amount of energy needed to exert a force of 1 Newton through a distance of 1 meter. This means that if Count Rumford wants to raise this kettle of water, which has a mass of 1 kilogram, or a weight of 10 newtons, through 1 meter, he'll have to expend 10 Newton meters of energy, or 10 joules of energy. But when we're dealing with heat as energy, instead of raising something through a distance, we raise its temperature through a certain number of degrees Celsius. In fact, scientists have worked out that it takes 4,200 joules of heat to raise the temperature of 1 kilogram of water by 1 degree Celsius. Let's see Count Rumford do just this with his kettle of water, which is now at 15 degrees. The Count is now moving the water with his egg beater. He's expending energy, and he's producing heat. Just enough heat to raise the temperature of the kilogram of water from 15 to 16 degrees, 1 degree Celsius. And it cost him exactly 4,200 joules of energy or heat to do it.
Take some hot water in a large beaker and some cold water in a small beaker. Place a thermometer in each beaker. Now carefully place the small beaker inside the big beaker containing water. Record the temperature of hot and cold water. We observe that the thermometer immersed in the small beaker shows an increase in temperature indicating a gain in heat energy. At the same time, the thermometer immersed in hot water shows a decrease in temperature as it loses heat energy. Thus, heat energy flows from a body at higher temperature to a body at lower temperature. Now record the temperature of both the thermometers after some time. Both the thermometers show the same reading, indicating that there is no transfer of heat. The state at which temperature of two bodies in thermal contact becomes equal is called thermal equilibrium.
If you stir a boiling liquid with a plastic ladle, after a few moments, the ladle will become quite warm. The same will happen with a wooden ladle. And a ladle made of metal can even become too hot to handle. This is because the heat from the boiling liquid is able to travel up the length of the three ladles quite slowly through plastic and wood, and very fast through metal. But how does heat manage to do this? How does heat travel through things? Well, when the hot liquid heats up the end of each ladle, its molecules, or in the case of metal, its individual atoms, start to vibrate more rapidly. And when the heated molecules, or heated atoms, vibrate faster, they start bumping faster and faster into their slower neighbors, causing them to speed up in turn and bump into their neighbors, and so on all along the ladle. In this way, the increased speed of vibration, and therefore the heat, is passed on from molecule to molecule, or from atom to atom. It's like a row of dominoes knocking each other over. And this domino effect, which leads or conducts heat through any substance, is called, naturally enough, conduction. Non-metals, such as wood and plastic, conduct heat quite slowly. They are bad conductors of heat. In contrast, all metals conduct heat very rapidly. They are good conductors of heat. That's why the witch with the metal ladle got burned. But why is heat conducted so much faster through metals than through non-metals? Why are metals good conductors? What's their secret? Well, the secret lies in the fact that there's something very peculiar about the atoms in metals. We know that all atoms consist of a nucleus with a number of electrons whizzing around it, as in this very simple model. And we also know that the nucleus exerts a force of attraction on these electrons to make sure that they don't go wandering off all over the place. But if it were possible to look very closely at a group of atoms in the metal ladle, we'd see something like this. There are a lot of electrons that don't seem to be attracted to any nucleus. They're shooting about extremely rapidly in all directions. It's like this in all metals, in fact. They all have these free electrons, which are quite independent of the atoms themselves. Now look at what effect free electrons have when the end of the metal ladle starts to get hot. Not only do the atoms start to vibrate faster, But the free electrons also speed up and begin to move faster still, colliding with the atoms more and more often and with more and more force. And each time a free electron bounces off an atom, it causes that atom to vibrate a little faster. Imagine that the atoms were pins in a pinball machine, and that each of the free electrons were one of the pinballs. Each time a pinball hits a pin, the pin lights up, just like an atom vibrating faster. And the more rapidly the pinball moves, the harder and more often it bounces against the pins. If you could fire dozens of pinballs simultaneously, you'd be lighting up the pins like crazy. You'd be producing the same sort of effect that occurs when the metal ladle is heated. Only in the case of metal, of course, there are millions and millions of free electrons to speed up the vibrations of the atoms, and therefore speed up the spread of heat. And that's the secret of why metals are such good conductors. Much better than plastic or wood.